Good day, everyone. I'm going to be solving a problem here that somebody has asked me for a little bit of help with. This is from Physics 20, and the first part of this question is a classic problem in Physics 20. You have two masses, they are unequal to each other, and they are draped over a frictionless pulley by connecting them to a piece of quite strong string. And the first question, which is a classic kind of question in Physics 20, is if I release them from this state, what will the acceleration of the masses be? And then the second question is a little more nuanced, I suppose. We're asked to find the tension in the string. So to begin with, for question A, if you want to determine the acceleration of the masses, then you need to draw a free body diagram showing all of the forces acting on the masses. And there is a force of gravity acting downward on the 3 kilogram mass, and there is also a force of gravity acting downward on the 5 kilogram mass. And clearly the force of gravity pulling the 5 kilogram mass down to the surface of the earth or to the floor is greater than the force of gravity pulling the 3 kilogram mass to the floor. So your free body diagram will look like this. We're going to put some labels on it. This is the force of gravity acting on the 5 kilogram mass. This is the force of gravity acting on the 3 kilogram mass. And for all of these problems where you either want to find an acceleration or a net force acting in a system where there are multiple forces, you draw a free body diagram so that then you can create an equation. And the equation is always going to be that the net force is equal to the sum of all of the forces. Net means total. So the net force in this system will be the sum of the gravitational force on the 5 kilogram mass and the gravitational force on the 3 kilogram mass. So we need to add those two forces together to get the net force. And how you add forces, since forces are vectors, depends on the directions of the forces. If you had two forces which were acting in the same direction, then you can find the net force by simply adding the magnitudes together, by adding the two amounts together. Well, when you look at your free body diagram that we've got here, those two forces really are in the same direction. They're both downwards towards the floor. But due to the nature of how they're connected to each other, they are what we would call opposing forces. So the force of gravity pulling down on the 5 kilogram mass is forcing the pulley to want to rotate clockwise, whereas the force of gravity pulling down on the 3 kilogram mass is opposing that, and it's wanting or trying to pull the pulley in a counterclockwise orientation. And as a result of that, these two forces oppose each other, and when you add two forces that are in opposition, you add them by taking the larger magnitude and subtracting the smaller magnitude. So what we're going to do here is now adjust this and say the magnitude of the net force is going to be equal to the magnitude of the force due to gravity on the 5 kilogram mass minus the magnitude of the force due to gravity acting on the 3 kilogram mass. Now this is just the way I do it. You could certainly do it by writing the following: F net without a vector symbol equals Fg on the 5 kilogram mass without the vector symbol minus Fg of the 3 kilogram mass without the vector symbol. These two equations mean the exact same thing. This equation, which will be highlighted in blue, and this equation, which will be highlighted in blue, mean the same thing. It's just a different notation. So again, the equation at the top is saying we add the forces, and forces are vectors. The two blue equations are just different ways of saying what we're going to do to the magnitudes. And the bottom line now is we end up with the following equation we can use to solve this first problem. MA equals mg minus mg. And again, because we're dealing with magnitudes, we're not going to put any directions in. We're not going to, for example, put in for G negative 9.81. We've already taken that direction into account. The other thing, of course, you need to be aware of is that these three masses are all different. This mass with the MA is 8 kilograms. If you want to determine the acceleration of the entire system, then that MA will be MA of the entire system. So we're simply adding that 3 kilogram mass and the 5 kilogram mass together to get 8 kilograms. And then over here we're going to have 5 kilograms times 9.81. You can use meters per second squared or newtons per kilogram minus 3 kilograms times 9.81. And again, I'm choosing to go with meters per second squared here, but you could use newtons per kilogram. Finding the acceleration here is pretty straightforward. You're going to calculate what 5 times 9.81 minus 3 times 9.81 is equal to. So 5 times 9.81 minus 3 times 9.81. What this is the net force acting on the entire system. Of course, that's equal to 8 kilograms times A, so you have to divide by 8. And we get 2.4525. I'm going to carry all my decimals here to make a point. This is meters per second squared. To make a point when it comes to finding the tension. So if we take a look at the solution to that first part of the question, we draw a free body diagram, which is shown on the right. We use that free body diagram to come up with a net force equation. Net force is always the sum of all of the forces. Then we say, well, how would we add those two gravitational forces? Well, we would subtract the magnitudes because they are opposing each other, and that leads to the solution. Let's take a look at the next part of this question, which is, what is the tension in the string? Now, when you're determining the acceleration of the system, you have to look at the free body diagram of the whole system. There's kind of a trick you can use here to find the tension in the string, and it's that you can either draw and use a free body diagram for the 3 kilogram mass or for the 5 kilogram mass. And you will get the same result no matter what. So I'm going to do it first using the 3 kilogram mass. We're not looking at the 5 kilogram mass here. We're looking only at the 3 kilogram mass. And the net force on the 3 kilogram mass, and I'll go with magnitude of the net force. We'll include the direction in a second. Will be equal to 3 kilograms times that acceleration that we've determined. And I want to go back and just talk about that acceleration that we found in the previous question. I suppose I haven't really, well, I have answered the question. The magnitude of the acceleration of the system is 2.4525. I believe there was a 5 there as well, yes, meters per second squared. But what that means is the 3 kilogram mass will accelerate up. The acceleration of the 3 kilogram mass will be positive 2.45 meters per second squared. Whereas the acceleration of the 5 kilogram mass will be negative 2.45 meters per second squared. Because the 5 kilogram mass is heavier, so it's going to move down, and the 3 kilogram one will move up. So this acceleration of the 5 kilogram mass is negative. This becomes important because you need to appreciate that the net force on the 3 kilogram mass is up. The net force on the 3 kilogram mass has to be up because it's going to accelerate up. So let's see what we get. So take my calculator. I'm going to take 3 multiplied by our acceleration, and I get a net force on the 3 kilogram mass of 7.3575 newtons, and I'm going to throw the direction in now. I'm going to say up. This is the actual net force with the direction. Again, it's only on the 3 kilogram mass. Well, now let's look at the forces acting on the 3 kilogram mass. There is a force of gravity acting down. But since it's accelerating up, there must be a force upward on the 3 kilogram mass that is greater than the force of gravity down. And that force upward is the tension, what in high school physics is sometimes called the force of tension. In post-secondary, sometimes we just call it capital T for tension. So this is what we are after in this question. And when we take a look at this free body diagram acting on the 3 kilogram mass, the net force is going to be the sum of these two forces. Let me repeat that. This net force has to be the sum of these two forces, because net force means add together. So what that means is, well, how would we add those two green highlighted forces? You would take the force of tension, its magnitude, and subtract the magnitude of the force of gravity. And that would give you the net force. The magnitude of the net force. This gets a little bit tricky. The only reason why we are focusing on this direction here is so that it leads us to this free body diagram telling us that there must be more force up. So we've calculated the net force. It's 7.3575 newtons. This has to equal the magnitude of the tension minus the magnitude of the force of gravity on the 3 kilogram mass, which is 3 kilograms, times 9.81 meters per second squared. So mathematically looking at this, we have to take the 7.3575, and to get Ft by itself, we're going to have to add to that net force of 7.3575 whatever 3 times 9.81 is. So I'm going to add 3 multiplied by 9.81, and I get 36.7875 newtons. Okay. So that's the tension in the string, which would be rounded to 37 newtons. I want to just take an opportunity here to review what we did. To find the tension in the string, we say that the tension in the string is the force applied upward to the 3 kilogram mass, which is opposed by the force of gravity acting down. So we come up with this formula. Net force has a magnitude of that upward force minus the force of gravity, and it leads us to the answer. But I started this by saying it doesn't matter which mass you use. So let's try the same thing again, but this time we're going to focus our attention on the 5 kilogram mass. So we've already done it for the 3 kilogram mass. Now what we're going to do is do it for the 5 kilogram. Well, there is a force of gravity that is acting down. On the 5 kilogram mass. And there has to be a tension upwards, otherwise the 5 kilogram mass would be in free fall. Except that when we determined the acceleration of the system, we said it had a magnitude of 2.4525 meters per second squared. But when we're talking about the 5 kilogram mass, this is down. The 5 kilogram mass is accelerating down. Let's keep that in mind. If the 5 kilogram mass is accelerating down, then this applied force upward on it, which is the tension, has to be smaller than the force of gravity. So this is the tension in the string, which is the applied force upward on the 5 kilogram mass. The net force is the sum of those two forces. So how do we add these two forces? We take the magnitude of the larger force and we subtract the magnitude of the upper force, or the, not the upper, well, it is the upper force, but the smaller force. So if I just go back and look at what we did with the 3 kilogram mass, our net force, this is highlighted, or it will be highlighted for you at the bottom of the screen, this net force on the 3 kilogram mass, and my computer is lagging a bit, so we'll just give it a second to catch up. The net force is the force of tension minus the force due to gravity on the 3 kilogram mass, because the force of tension has to be greater than the force of gravity, so it will accelerate up. Since the 5 kilogram mass is accelerating down, our equation is now different. Because the force of gravity down is greater than the upward opposing force, we take the magnitude of the force of gravity minus the tension. So let's go ahead and put the numbers in. F net is MA, so that's 5 kilograms multiplied by the 2.4525 meters per second squared, equals FG is mg, so that will be 5 kilograms times 9.81 meters per second squared, minus what we're after. So now we have to solve that. Since it's minus Ft, I'm going to add it to the other side where it becomes positive. I would rather find a positive quantity than a negative. And it would be whatever 5 times 9.81 is. I'll just leave the units out because we've already got them. Minus 5 times 2.4525. So 5 multiplied by 9.81 minus 5 multiplied by 2.4525 gives me, and this is why I wanted to keep all my units, gives me the exact same answer. So the tension in the string, regardless of which mass you're using, is approximately 36.7875 newtons. And you can choose to round that however you see fit. That's not the point of this video. So the tension in the string is 36.7875 newtons upwards when we look on the left side of the diagram, and it's the same force upwards when we look at the right side of the diagram. You want to try to remember in a Physics 20 level that tension in a string is the force that the string is applying to the object. So that's the solution of the question. Once again, just to review, when you're finding the acceleration of the system, you look at the forces on both objects and you use them to build a net force. Then when you want to include the tension, you look at only the forces acting on the 3 kilogram mass or on the 5 kilogram mass. It's interesting to note that I've actually lied to you a bit here, because we did not, in part A of this, I did not draw all of the forces. I didn't draw the two tensions because I know they would be equal but opposite. So that's the solution to both of the questions. I hope that you found that helpful. Take care.